Okay, so thank you very, very much, Emmanuel, and thank you very much for the invitation. I'm very happy to be here and discuss about the work that we are doing with several colleagues from INRIA, University of Lisbon, CNRS, Ecole, Polytechnique, and several interns, engineers, and I will also mention the names in the end. So first of all, how did this project start? Let's try first to understand what is a conflict of interest. So a conflict of interest, according to the French transparency law, which was established in 2011, a conflict of interest is any situation where a public interest may interfere with the public or a private interest in such a way that the public interest may be or appear to be unduly influenced. So this is the language that the law people are using. So for us, I think that we more or less understand. So we mean that if there is a person in a regulatory authority, for instance, we don't want this person to also receive funding from an industry which asks, for instance, to get authorization for a product, right? So we wouldn't want, for instance, someone from Pfizer to be in FDA and then give authorization for Pfizer vaccines. So this is what this whole thing is about. And unfortunately, this is not always the case. So we do not always have this kind of objective, let's say, regulatory authorities. And there are investigative journalists who are investigating this kind of relationships that we have between people who make decisions and potential conflict of interest like funding. So we are lucky to be working with one of such journalists who is Stéphane Aurel from Le Monde. She has also received an award for her work on the Monsanto papers, a European Investigative Journalists Award. And it is very good because she is also giving us some guidance and what we should be looking for. So what I will be talking about in the following is based on true data and real world use cases. Of course, the whole project had started by Joanna several years ago. So I will be discussing more about the things that I've been doing when I joined. So first of all, let's discuss where can we have some conflicts of interest. And the first domain that we are investigating is the biomedical domain. So here we have experts in the biomedical area who advise national and international officials on decisions with impact on public health. For instance, the approval of COVID-19 vaccines, but of course, there are many others like drugs, vitamins, any kind of products that are related to health. And then on the other hand, of course, we have a very large industry with interests in the area, and they may recruit experts who are likely to be auditioned by the regulatory boards. So the goal here is to establish a database of conflict of interest where it would be easy to find the declared links of Dr. Alice with the health star. So we don't want someone who has a conflict of interest with the company to give an opinion on a product which is produced by that company. And I think that this is to the best interest of both the people and the company, so that in the end we have some very, very clear opinions on the products. And of course, there is more. There is also the public administration domain, and I will be discussing about the use case from there, where elected officials are making decisions about public money, and then they are signing contracts with companies. And then companies with interests in the contracts may try to corrupt the officials. Unfortunately, this is something that we have been seeing with different use cases. So the goal here is to establish a database of conflicts of interest where it would be easy to find the declared links of Mr. and Mrs. Smith with Anadiotis contracts. So this is again, more or less the same idea. And in order to do that, we need to use data which are usually available, but technically buried. And when we say buried, we have to look into papers so that we find acknowledgements. We need to see co-authors in other papers. We need to see text like other articles on the web where people are mentioning their funding or try to discover this kind of relations. So the idea here is that there is a lot of heterogeneity. Just to bring an example, here in France, there was some years ago the Balkany Affair. So here, that was a political financial affair involving Isabelle and Patrick Balkany, who were respectively the first deputy mayor and the deputy mayor of Levallois-Perret, which is a town on the north side of Paris. So, long story short, the thing is that this couple was found, there was some suspicion of corruption against Patrick Balkany, and for whom they suspected of having bought a luxury villa in Marrakesh, thanks to 5.25 million euro, which was donated by certain businessmen in exchange for Patrick Balkany's award of contracts in Levallois in Namibia. So all this, you can find this information in the webpage from Wikipedia that I mentioned here, of course. That is an old story, and then you can find, of course, everything in the news. And now let's see how we can work things out with this kind of affair. First of all, we have what you see here on the top left-hand side of this slide is a list from the Public Officials High Transparency High Authority. So there do exist these kind of records within the French state. So here we have that there is a name, an owner, location, and the type. And then, of course, there is more, like we have we have companies, we have owners, we have locations, so we have the type of activity. And then here we have some resources from DBpedia. So from DBpedia, which is a knowledge base, we can know that Marrakesh is a city in Morocco. We know that Morocco is a country in Africa, and we also know that the Central African Republic also is located in Africa. So we can establish some relationships from knowledge bases which are, let's say, widely accepted. And then on the top right-hand side of the slide, you can see the National Director of Elected Officials, which is written in JSON. And here we know that from Levallois-Perret, there is a mayor, there is a city council, and there is several other information. And finally, some text from Libération, which is a very well-known French journal from November 13, 2014. We can see some information about Balkany, Levallois-Perret, Areva, which is a company, Centrafrique, and some other keywords which appear interesting to us. So what we want to do in the end is to combine the data out of all those heterogeneous data sources and formats in order to be able to make some conclusion out of it. So the idea here is to be able to find connections among the Balkans and the whole situation in Morocco. So in order to do that, to give you a preface, we are loading everything into a graph. And what we say is that we want to find the connections among all the different terms, all the different nodes, if you will, that we are interested in, so that we can investigate them. Of course, we do not claim that we are going to solve all the problems, but what we do claim is that instead of having the end user studying all the different PDFs, all the different knowledge bases, and then being able to understand what's going on, which takes years and years of research, what we can do is to help to boost data exploration, to shed some light on the data, and then give some intuition, so that then the users, in our case the journalists, can work more, and they can work more towards a specific and more focused, let's say, approach. So in order to do that, we have a system that is called ConnectionLens, and we have a whole end-to-end graph processing pipeline. So what you see here in ConnectionLens is that we have a pool of heterogeneous data sources like PDF, JSON, RDF, XML, HTML, tabular, text. And we are, from all those data sources, we are constructing a graph. We are extracting the data using different policies in order to be able to do that. Then we are storing all the information about the graph in a relational database. And even from that point on, we can start querying that graph. And then, however, in order to make things a bit faster and investigate scalability, we have even used an in-memory, we have even gone in memory where we load the graph inside the main memory, and we have a parallel query engine. So overall, we have an algorithm which is used for querying the graph, which has been constructed and stored in the database. That database might be stored either in the disk or in the main memory. So let's take things one by one in order to explain to you how things are working in ConnectionLens. And let's start, of course, with the data sources. So the data sources that we are considering in this project can be either structured or semi-structured or fully unstructured. So we do not necessarily consider RDF, even though that might have been a bit easier, because in the end, we want to help real users. And we know that in our case, this is in order to do that, we need to work with JSON files, and we need to work with PDF, which has been extremely challenging, by the way. And moreover, this project also has started by considering the discovery of fake news. So this is another use case that we cover. And for this reason, it is absolutely necessary that we work also with fully unstructured data. Moreover, the data sources that we are using can be extremely dynamic. So we have projects that started and abandoned as per news cycle and data availability. So this means that sometimes we have some journalist, for instance, who is interested in a specific topic they're investigating. But then something else pops up. So perhaps something more interesting, perhaps they cannot find enough data, so they have to freeze the project. Perhaps their editor-in-chief tells them that they should change their focus. So we need to be able to handle this case that our graph might have to adapt by unloading some data sources and loading some others. Moreover, we have no schema. And the data producers are also often non-collaborative in the sense that sometimes it is hard to communicate, in the sense that we may be speaking a different language, which is, I think this is something that holds for many different cases. And also sometimes they don't have enough time because they also have to produce their own work, and that's why it's not very easy all the time to be able to devise a common schema so that we can work with the data. And finally, for most journalists, databases do not come very naturally, and IT support is very limited. The scope is different. They have the databases in the sense that they have you can imagine that they have a repository of articles, they have a repository of files that they discover coming from, I don't know, like the sources like Panama Papers or whatsoever. But it's not that they have a lot of structure in there. So they mostly know keyword-based search. It's what most people are used to by doing Google. So what they would like to do is to just write some keywords on what they're interested in, and then have some guidance from the system in order to be able to do more focused search. So let's say that we are trying to filter out a big part of the data. So the whole idea here is what we conclude from all those is that we have to integrate heterogeneous data sources in a graph, and then we need to query that graph by using keyword search. So let's see how we can construct this graph so that then we can continue with querying it. Okay, so first, so the graph construction takes place in several stages. The first stage is the primary node and its construction. So here we are reading the different files like XML, HTML, JSON, RDF, and we can from those files that already have a graph structure, it is, let's say, very easy to go and generate a graph out of them, since it is something that happens natural. It is also quite easy when we have relational tuples. So in this case, we are using a one-to-one mapping between the tuples and the graph nodes, and all the primary key, foreign key constraints that we have, we model them as edges on the graph. So it is, again, something quite straightforward, as you can imagine. And then we are converting PDF information into JSON for the text content and RDF for the tabular content, so that we can then be able to load the data into the graph. Now, of course, depending on what we want to do, we may not have to convert the whole PDF document. Maybe sometimes we just have to focus on a particular part of it. For instance, when we are looking for conflicts of interest, and when we are looking for funding which has been received by the authors, or for relationships between between authors who are in public authorities and authors who are in the industry, we are interested mostly in the author list, the affiliations, the acknowledgements, these parts of the paper, so we don't have to go through the whole thing. So by using this kind of information, we can end up having this part of the graph that you see here, and it is just a part of the graph that I showed you earlier. So here you can see that from a JSON file, from the JSON file where we were discussing about the city council, you remember that we had this JSON file with the directory of the elected officials. We can extract the nodes that there is a mayor and there is a name in the city, Levallois-Perret, there is a city council, and then there is a member in the city council with the name Balkany, and so on and so forth. Then on the second stage, we have the entity extraction. So here, for every text node in every data source, we create an entity node and we make it a child of the corresponding text node. So here we are extracting the entities out of the text. So here, effectively, what we are doing is that we are starting to give meaning to all the text that we have discovered or we have loaded in our data. And in order to do entity extraction, we have experimented with different techniques like the Stanford NER library. We have in the team has also developed a custom entity extractor supporting English and French based on Flare, whereas the data extraction is based on idle time. So for this, we have colleagues that have been intensively working on that. Oana Balalau has also been working on that, and we have several PhD and master students who have worked on the entity extraction. So by doing the entity extraction, what we have is the nodes that you can see here below. So if you go back and you see the graph that I showed you in the beginning, now we have the extracted entities here. So we have Balkany, Levallois-Perret, and Balkany here as entities. And now that we have those entities, we can start working with them. And what I mean by that is that we can move one step further and do a disambiguation. So now that we know that we have something that has a meaning, we need to understand exactly what we mean by that. So disambiguation is needed when we have a word that can be used with different meanings. So for instance, in France, the former president before Emmanuel Macron was François Hollande. Now, Hollande in French also is the country, Holland, the Netherlands. So here when we use the word Hollande, we need a module which will tell us whether we mean Hollande the president or Hollande the country. And then, of course, there are many other similar situations. So for this, we have introduced a stage in the pipeline which does the disambiguation. So this pipeline is based on Ambiverse, and it's using knowledge bases such as Yago, Wikidata, and Wikipedia, and it is helpful on well-known entities. And then the last part that we need to do for the construction is node matching. So the thing is that we have some nodes which have the same or similar labels. So for this reason, we have the good old same as edges, which are used to connect the nodes with the same or similar edges. And then we put a score on those edges, we put a weight on those edges, which reflects the similarity score based on a given function that we may be using. So this is something that the user may select. Now, the problem with that, we can do that when we want to be extremely rigorous and fine-grained, but the problem here is that we have a quadratic cost in order to be able to scan the whole graph and then introduce all the same as edges, right? So for this reason, we have introduced a heuristic which does a node factorization, meaning that we create only one node per document or per graph for every label that we find. So we consider that everything which is considered in, for instance, in one document, all the nodes that have the same label, they correspond to the same thing. Of course, we may lose some information, but on the other hand, the graph may grow extremely large. And then the querying problem that we have is anyway NP hard. So it's not that we have the luxury to, be extremely exhaustive. Of course, the system allows it, but we do not use it very much in practice. So by following those 4 stages, we have now constructed the graph. We have generated the nodes and the edges, and we have pushed the data inside the relational database. So now that we have our beautiful graph and we have the data that we want to query, we need to start worrying about how we are going to use it. So now we are going to look at how we are able to query our graph. And I am going to start discussing what is happening here with our keyword search algorithm when we are using it over the relational database using a single-threaded version. And then I am going to move on to the optimized graph layout and the in-memory migration for parallel querying. So now, what we have is a graph built of nodes and edges, which have been generated as I explained earlier. And we have a set of keywords provided by the end user, in our case, the journalist, and they return the k highest score minimal answer trees. So here an answer tree is, we call an answer tree a set of edges, which first of all form a tree. And second, for each keyword that we have, they contain at least one node whose label matches the query keyword. Effectively, what we say is that we want trees that include nodes matching, whose labels match all the keywords that we have. So we don't want to have any keyword left behind. On top of that, we are interested in minimal answer trees, meaning that if we remove an edge from the tree, then it should make it lack some query keywords. So this way, it means that we cannot have any smaller tree than that. That matches the whole, that answers the whole query. And if a query keyword matches the label of more than one node in the answer tree, then all those matching nodes must be equivalent. So they must be, for instance, connected with the same as edge. So by this, we mean that we should, if we combine all the nodes that match a given label into a single node, then this means that every answer tree will have only one node matching every keyword. So these are the requirements that we have for our algorithm. Clearly, the problem is related to the group Steiner tree problem, because we have some keywords, we have a graph, and then we want to create trees out of it. So this is clearly related to the group Steiner tree, so it isn't hard. But on top of that, we are making it a bit more interesting, or a bit more challenging, if you will, by saying that the graph should have bidirectional edges, because the direction here in the way that we are constructing the graph does not make much of a difference. So we cannot the way that we will be putting the direction of an edge on the graph that we are studying might change the meaning. So we don't want that. We just want to find some connections. Furthermore, we are interested in finding the k smallest trees, in the sense that the user will give us this k number up front. And we might have several nodes matching every query keyword. So in that, we are considering a very, very generic version, which, however, is the version of the problem that matches the requirements of our users. So in order to be able to address this problem, we have developed the grow and aggressive merge algorithm. So this algorithm has two steps, the grow step and an aggressive merge step. So in the following, I'm going to explain to you how this works through an example. So suppose that we have a query with m keywords, W1, W2, and Wn. And then suppose that we have that for every keyword, we have some nodes matching it. So for W1, we have nodes N11, N12, blah, 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 N1, K1. Then for keyword 2, we have node 2.1, 2.2, and go up to K2, and so on and so forth. So we have ki nodes matching each keyword wi. So when we want to perform a grow step, what we say is that when we are in a node, suppose that this node is node 1, 2, so it is this node here. When we apply a grow step, we are going from N12 to one of its neighbors. So let's suppose that this node is N2, 1. And then let's suppose that there has been another tree which has been created in another grow step, which involves node N21, which is the root of a tree, and then it has nodes N31 and N32. These nodes, of course, those connections are connections that belong to the graph. So effectively, we are doing something like a BFS, if you will. We are sitting on a node, we're saying, I have some neighbors, I am going to grow towards a given neighbor. So now I have a tree, and then I'm going to grow again, so the tree becomes larger and larger. When we have two trees that have the same root, then, like in the case we have here, then we apply the merge step. And after we have merged, we have one tree which has a root, the root which was the root of both the initial trees, and it now contains all the nodes here. So as you can imagine, by using this process, we can end up having the nodes that we're interested in, and they should be all connected in a tree. Clearly, our search starts from the nodes that match our keywords. So what we do first is that we perform a query on our database, we find the nodes that match the keywords, we start from those nodes, and we start growing. And when we find a merge opportunity, then we merge the trees. And that's how the algorithm keeps going. So in order to give you an example on the graph that we had before, suppose that we want to run a query that has as keywords Africa, real estate, and Balkany. So let's see how we go. So here we have the keywords. Sorry. So here are the three keywords. We have Africa, real estate, and Balkany. So the first we apply the growth step. So you see that from this node we grew here, from this node we grew here, and from this node we grew here. And then in the second step, we say that we are now considering this node. We have a tree which has this node and this node. From Balkany, we reached this node, and then we are growing again. We reached that node, the node that you can see here. And now we are growing again. We are reaching this point, and now we are growing again, and we're reaching this point. And now we are growing again and we are reaching this point. So you see that as long as we don't have any merging opportunities, we can only grow. So it's like discovering what's going on in the graph. So we are doing an exploration. It's not that we can do much more. So now we apply another grow operation, and you see that we went from this node here to this node here. And now we apply another grow step and we go to Marrakesh. And another growth step to where we go to the entity Marrakesh that we have here, and here we apply another growth step on the Marrakesh that we have from DBpedia. Now, what is interesting to notice here is that we have a connection between what was given in the CSV file about the different public authorities and DBpedia. So this connection was based on Marrakesh, the two words that are effectively the same. So since they are the same, we are putting a same as edge, and this edge is effectively connecting the two data sources. So now that we were able to pass through this edge, we are moving here, we are applying another growth step, and here another growth step. And here now we have another growth step. And now we can merge the two trees. We can merge this tree and that tree. So here you can see that we apply a merge operation. And now we have our first tree that connects Africa and real estate, which were two of the three keywords that we were searching with. And then we can continue with the search. So after we have merged, then we have our new tree and we grow here. And now we are going back and we are growing towards this direction and then this direction. And then we are continuing growing and we're reaching this point. And now we have, again, the same thing where Centrafrique is, we have identified that it is pretty much the same as Central African Republic. So here you see that we have a weight of 0.85. It's not exactly one, the weight of the same as edge, but we know from our knowledge bases that these two should correspond to the same thing. So now we are connecting with this node, and now here we can apply our second merge operation. So now we have a tree which connects Africa, real estate, and Balkany. And this tree contains data that come from heterogeneous datasets. And the way that we have used in order to bridge those heterogeneous datasets is through the same as edges that we were using. In order to be able to use, of course, those same as edges, we need to be pretty sure as we can be, that those nodes correspond to the same entity. And that's why we apply all those different stages like entity extraction, disambiguation, and the introduction of the same as edges. Because this way we can treat the different data sources as a unified graph. And this way we can have our results. So now the question is, do we grow or do we merge? Because as you saw before, we have several nodes that we start from, and we start growing from some nodes, then we grow from some other nodes, and then at some point we merge, and then we continue growing. So things are not, so things need to be cleared out, and of course we cannot be completely arbitrary in our decisions. So what we do is that we assign priorities to the answer trees that result from the grow and merge operations. And we prefer, of course, the trees that match many query keywords. And then if we have trees, several trees that match the same number of query keywords, then we prefer trees of smaller size. This is only heuristic. It's not, of course, necessary, and it does not affect the correctness of the algorithm and the completeness. But nevertheless, we have, from our discussions, first of all, from our experience, we know that the search may never end. So it might take really a lot of time. So what we want is to at least provide a solution very fast, very quickly, give some solutions quickly. That's why we prefer trees matching query keywords, so that we reach quickly at least some answer. And then we prefer trees of smaller size, because if we have very large trees, then it is not easy for the user to follow up on the search and then cross-validate that everything was correct. We don't want to have very long paths between two keywords, for instance, that exist in the same query. So what happens is that every tree which we build is pushed inside the priority queue. So we have the priority queue here. After the merge operation that I showed you before, we put the tree here. We apply the rules of the priority queue. So, and then we pop from it, we grow the tree, and we merge with the same rooted answer tree. So this is effectively the process that we follow for GAM search. Now, but the problem in the graph is that since we might be reaching the same point in the graph by taking many different directions. So the same answer tree may be created by following different combinations of grow and merge operations, which of course incurs duplicate work. And in order to avoid the duplicate work, what we do is that we maintain a history of the explored trees. And therefore, every time that we get a tree, we check with the history. Of course, we use hash functions and everything. We check with the history whether the tree has been generated in the past. And only if it is the first time that we use this tree, only then we move on with further examination, like we put it in the priority queue so that it will be checked at some point. So another thing is that since that grow and merge operations are always performed on the root of every answer tree. So the grow changes the root of the answer tree to the newly added node, and the merge maintains the root of the answer tree, but needs to find trees with the same root efficiently. So this gives us the flexibility to be able to do an indexing based on the root, so that every time that we are looking for a tree to merge with, we can easily find it by using a hash-based index here. And now that we have our algorithm and we can find some connections, we decided to try to scale. And we decided to scale up before we scale out. So in order to scale up, we said, okay, let's try to play with in-memory databases. So in this case, we considered that several graphs can fit in the main memory of modern servers. So we said that we implemented a script to migrate the graph from the database, for which we use Postgres, inside an in-memory database that we implemented from scratch. And in order to implement the things in the in-memory database, we had to face two fundamental challenges. First, to decide the graph layout for the main memory and how we are going to parallelize the search. Keeping in mind that the graph is constructed from real-world data, and therefore we can make no assumptions about the partitioning. So the layout of the graph inside the main memory is what you can see here on this slide, where we have an edge table with the source node, the target node, the specificity, and several metadata about the edge. Here, the edge metadata are kept in a different table because we're not sure about the size of the metadata. Every edge might have different number of metadata, so that's why we keep a separate table for that. Then we have a node table with the source, the representative, meaning that we use one node as a representative when we have several nodes connected with the same datasets, several connections, metadata. Here we have the node metadata and the node connections. I'm not going to go into more details. The whole idea is that we keep the minimal information which is needed in order to be able to query this graph. And finally, we have a keyword index. So for this, we are using, we can apply, of course, exact match and prefix matching on the keywords. So by first, when we query, we first go to the keyword index. The keyword index gives us the nodes, and then we put the nodes that we find from probing the index in the priority queue, and then we start from the priority queues to search the graph. So we use a row major CVU cache-friendly data layout for our database. And now we have to start searching. So searching in graphs is ideally, generally, when we want to do something in parallel, we would like to partition our data. However, with graphs, it is already expensive to do a min cut before we start our search in order to have our partitions. And the problem is that we even can make no assumptions on the shape of the graph, because the shape of the graph is fully unknown because we use real world data. So this is something completely arbitrary, and therefore we cannot make any assumptions. Now, BFS-based approaches have already shown poor scalability, and the grow operation, as I told you before, this whole grow operation does resemble a bit of BFS. And then, but on the other hand, we know that the problem in our parallel search is the size of the intermediate results. So here, even though we know that parallel graph algorithms have issues with random accesses, or which is the main thing in memory processing, here we saw from our profiling that random accesses are not that dominating. So the problem that we have here is to be able to find quickly the nodes that we need to match with to apply the merge operations. So this is where most of the time is going. And moreover, we observed that our algorithm did not have any concurrence issues. And that's why we, instead of parallelizing, instead of partitioning, we went for extremely fine-grained concurrent data structures. So here we split our data structures into shared and private. So the shared data structures include the index, the history. So here we have all the worker threads writing in the history. And we have an index about the answer trees that we have built so far. Like, for instance, for W1, W2, we have those trees. For W3, W4, we have those trees, and so on and so forth. Whereas each thread, its worker thread, maintains its own priority queue. So this way, every thread is popping a tree from the priority queue. It applies the grow and merge operations by using these shared data structures. And when it's done, it pushes the new tree in the priority queue and moves on. If a priority queue of a thread is done, it is empty, then it gets data from another priority queue, from another thread. So we applied work stealing because we cannot be sure about the load balancing since the graph is completely unknown. And to show you some numbers about what we've been doing, we have, of course, we have been using our engine with in several contests. We have users who have been using it. Here I'm going to show you some evaluation results over synthetic and real-world datasets and workload. We're using a two-socket Broadwell server with 192 gigabytes of main memory. We have implemented the in-memory database from scratch in C++ using NUMA-aware memory management and custom lock-free and relaxed consistency data structures so that we don't have any overheads from parallelization. We don't have any concurrency issues, any waiting on locks, and so on and so forth. For the results that I'm going to show you, we are using synthetic datasets. First, the chain and the star graphs. A chain graph looks like this. So here we have one node that is connected with an edge to the next node, then an edge to the next node, and so on and so forth until we reach the end. And we have backward edges. By doing this way, as you can imagine, we are exploding the search space because we have two edges on connecting every pair of nodes. And we are placing the keywords that we are searching at the two edges of the chain. Excuse me. And on the other hand, we have a star graph where we have one node effectively representing the end of, we have several lines. Every line has in the beginning one different keyword. That's why you see keyword 1, keyword 2 up to keyword P. And on the other side of the line, we have the same keyword. Given that we have the same keyword here, all those nodes are connected with the same as edge. And so we consider that all those nodes correspond to just one node. And that's why all those constitute a star. Here is the performance of our engine. On the x-axis, you see the number of threads going up to 20. On the y-axis, the time in thousands of seconds. And we are experimenting with different graph lengths for the chain from 12 to 15 nodes. So the thing here, of course, is that the size of the intermediate results is huge because the search space is exponential to the chain graph length. So effectively, we are generating a lot of intermediate results, and that's why you see that we are not growing very large the chain graph. Of course, this is the reason why we use the chain graph is to stress the concurrent data structures. Here we have a lot of threads which are accessing the history of the search and the priority queues concurrently so that they move on. So here we show that we have more than 3x speedup, which shows that we can scale pretty well. And on the star graphs, we have more than 3x speedup. Here, the star graph we go from 1 to 4 threads because we are using 4 keywords maximum, so it doesn't make sense to have more threads than that. And here you see how many nodes we have per branch. We are going from 1,000 to 5,000 with step 1,000. So again, we are scaling pretty well. It's not, of course, fully linear, but it is always graph search, so we cannot expect much more than that. And finally, the conflicts of interest idea. Here we did the work with a real-world data set. We extracted data from articles in PubMed and found connections among authors and company. So that was in collaboration with Stéphane Noël from Le Monde. So we used different documents from XML, JSON, and HTML. In total, our graph had more than 38 million edges, 23 million nodes, 1.7 million person nodes, 870,000 organizations, 157,000 locations. I'm not going to tell you, of course, the queries that we asked because they were completely arbitrary and we don't want to give up names and everything. But here what you can see is keywords where A corresponds to author, H to hospital, I for industry. And here you can see the keywords, the time in milliseconds to the first solution, the time to the last solution, the total time that it was running with a timeout of 60 seconds. So here you can see that we hit the timeout. And here how many solutions we have been able to find. And then the number of data sets that those solutions span to. Meaning that here you can see, for instance, when I use keywords author 1 and author 2, I find my first solution after 200 milliseconds, the last solution after 4.8 seconds. We found 1,000 different connections, different trees that connect those authors, spanning from 1 to 6 different data sets, and most of the solutions that we found span to 5 different data sets. And then things become more interesting. So for instance, here you see that we have an author from two different institutes, and then one public institute. So here we found, for instance, 9 different connections, so not that many, which makes it also interesting because they can be further investigated, where we have to go through a lot of different data sets. So in conclusion, what I showed you today is that there is a class of end users that prefer to use simple queries like keyword search, which is more intuitive to them. That the ConnectionLens is an end-to-end pipeline that integrates heterogeneous data sources in a graph and find connections among those that span across all those data sources. And keyword-based queries can be answered using our grow and aggressive merge algorithm. Here's a list of publications that we have here, and if you go to the side to the webpage of the project, you're going to find way more, but those publications were the ones that this presentation was mostly based upon. Now, currently, we're integrating our ConnectionLens queries into a generic graph query framework, and this is something that it's almost there, hopefully. It is a work which is driven by our postdoc Madhulika Mohanty, and we're doing it together with Ioana Manolescu. And this is a non-exhaustive list of people who have worked on the different software that we have used that I have presented to you. And of course, there are many other interns, master's students, engineers, and researchers who have contributed with ideas and code in earlier stages of this project. As I told you, this project existed before I joined. It is led by Ioana Manolescu, so it is something that has been there. And you can find more in the Sources Say website, which is our currently funding project funded by the French ANR, which is something like the NSF for France, and the Ministry of Army. That was it. I hope I didn't work too much overtime, a bit. So thank you very much for your attention.